Uh, okay, I think now it is started, I think. Okay, red button has come. Okay. So shall we start or is Roshan Kumar removed or what?
Yes, I think so, sir.
Okay, you ask him to join. Okay, because once I start, I cannot see. Once I go to full screen mode, I can't see any. But with Smail, he can automatically join, no?
Yeah,
Yes, sir.
yeah.
Yes,
Okay,
Yeah,
okay,
I
they'll
think
he
join.
has joined
Okay,
back.
they'll join.
I'm sorry.
Okay, we'll.
I'm sorry, sir. I was thrown
No,
off the thing.
no, I think Google fault only. Okay, we'll continue with this. Okay, so it has wiped out my annotations. Okay, to continue with our lecture, the solution to this constraint optimization problem is the same as that for the unconstrained problem. So let us look at the unconstrained objective function like this. So unconstrained objective function means there is no constraints. So all regions are allowed. All these regions are allowed. Okay, that is from minus infinity to plus infinity. All regions are allowed. So then, how do you find the minima of this objective function? Okay, you just take the first derivative, equate it to 0, and find the value x star. Okay, so you can see that you get the same x star even if the feasible region is there. So this feasible region is not needed. Okay, does not change the um, solution. You get the same solution um, for this unconstrained problem as for the constraint problem. Okay, so if the solution to the optimization problem occurs deep inside the feasible region, there is no need to take into account these constraints. Okay, you can consider it as a unconstrained problem and you can forget this feasible region and you can just differentiate the objective function and find the minimum. So that is why these constraints are called inactive.
Inactive.
Uh, So if the optima occurs in the interior of the feasible region, constraints are called inactive. So you can just ignore these two constraints and you just take objective function, differentiate it and find the minimum. Okay. But you have to know in advance that the constraints are inactive. And you can know constraints are inactive only if you draw this figure. So if you just look at an objective function and two equations, you can't say if the constraints are inactive. So you have to plot them and find it. Okay. Then active constraints. Okay, what we do is that we shift this feasible region to the right. So now what is happening is that, okay, this is the new feasible region. Okay, so the minima will occur at the boundary of this feasible region. Okay, so this is the new minima. Okay, and if and for the unconstrained problem, this is the minima. Okay, unconstrained problem, this is the minima, and for the constrained problem, it is the green dot. So which is at a slightly higher level than this unconstrained problem. Okay, so in this case, G1x is called active constraint because the minima occurs on the boundary of this G1x. Okay, so one important thing is that, so if you know that G1x is active constraint and the solution occurs on the boundary of G1x, you just need to solve the equations for the intersection of G1x and the intersection of the objective function. Okay. So if we know a constraint is active, you just solve for the intersection of that active constraint equation and the objective function equations and you will get the solution.
Sir, but we'll be able to judge this only if this is the global minima or even without understanding that.
No, now we are looking only at global minima, only
Oh,
one minima. Multiple
okay,
minima should study later.
okay, okay, right.
Okay. So we are only interested in the solution in this range. Okay.
Okay, okay.
Okay, then another case is now the entire feasible region is shifted to left. Okay, so now the minima occurs at the intersection of G2 and the objective function. Okay, and if there are no constraints, this would have been the minima. Okay, this would have been the lowest point if there is no constraints. But because there is this constraint, this green dot is the minima. Okay, and that occurs at the intersection of G2x and the objective function. So if you know in advance that G2x is an active constraint, then you can totally ignore this G1x. Okay, and you can solve for the intersection of G2x and objective function. That is a simple algebraic problem, and you can get the solution. Okay, so concept of active and inactive constraint is important because if we know in advance that a particular constraint is active, we only need to solve the intersection of the objective function and that constraint equation. So if we know in advance that the constraints are inactive, we can simply ignore those constraints and solve as an unconstrained problem. That means just differentiate the objective function and equate first derivative to 0 and find the solution. So later we'll study, there are some complicated algebraic methods to check if a constraint is active or inactive, but those methods are as difficult as solving the optimization problem. Okay, then another type of function, two type of, okay, some definitions for objective function. First is called monotonic function. So monotonic function is one which is either continuously increasing or decreasing with x. So if you look here, okay, this function is continuously increasing with x. So the definition of monotonically increasing function is that if you take any 2 points x1 and x2, then f of x1 should be less than f of x2. Okay, within this range. Okay. Then monotonically decreasing. Monotonically decreasing means from the x1 to x2, that is from low value of x1 to high value of x2, the function is decreasing always. So if you take any two x coordinates, x1 and x2, then f of x1 should be greater than f of x2. Okay. So this is monotonically decreasing function. Okay, so the importance of this is that you have a function called unimodal function. Unimodal function is one which is monotonically increasing to either side of the minimum value x star. So it is monotonically increasing to the right of x star and it is monotonically increasing to the left of x star. Okay. So this is the standard definition that you can look later, but I am explaining visually. So you have the central point x star. On one side, it will be monotonically increasing and other side also monotonically increasing. So this is defined only within a limited range A to B. Maybe after B, it can start decreasing. Okay. So we are not concerned with the range of minus infinity to plus infinity. Only within that optimization range A to B. Okay. So what is the significance of unimodal function? The unimodality means it has only a function has only a single minima between A and B. Okay, so it has only one minima within this range A to B. That is within the range we are trying to do optimization. Okay. Outside this range, it can have many other local minima also. Okay. So if it, the another thing is that if it is monotonically decreasing on either side, it has a single maxima. Okay, so suppose you have point x star like this, and the objective function is monotonically decreasing on either side. It means that within this range A to B, it has only a single maxima. So that is the opposite of this minima definition. Okay, so what is the importance of unimodal functions? Many optimization algorithms say that it will deal only with unimodal functions. That means it can find only one minima within the search range. If there are multiple minimas like this, the optimization algorithm will fail. It may either find this one or this one. So when a optimization algorithm, like in the MATLAB toolbox, it will give in the description that it will work only for unimodal functions. It means that it assumes only there is one minima within the search range. Then topography of functions in two variables. That is how to visualize an objective function in two variables. So if you have two design variables, you get an objective function z equal to f of xy. So it will be a surface in 3 dimensions. Okay, so it will look like this. Okay, suppose this is x, this is y. Okay, so this is f of xy. Okay, okay, so it will look like a surface like this. This is f of xy. Oh, okay, so each value of f of xy will be the altitude. Okay, so this particular value of f of xy at x1, y1 will be the altitude or the z component, z coordinate. Okay. Okay, then so we get a 3D surface here. F of xy is a 3D surface. Then instead of 3D surface, it can also be visualized as contours of the function projected on the xy plane. Okay, so contours are obtained by slicing the objective function at various heights. Oh, okay, so let me wipe out some of these things. Okay. This is x, this is y. Okay. To get the contours, the objective function has to be sliced at various heights. And then you have to draw the projections on the xy plane. Projections will be circles like this. Okay, so now you have to project down all these things. So these are called contours. Okay. Okay, so this is the let's say f1, f2, f3, etc. So this is the contour corresponding to f1. This is the contour corresponding to f2. This is the contour corresponding to f3, etc. So you would have studied stress contours in the answers. So this is like the like a map. Okay. So if you look at map of a mountain and all, they will give the altitude contours like this. Okay. Okay. So looking at the contours, we can see the trends of increasing and decreasing f of xy values. Then contours are to superimposed on the feasible region to graphically solve the two variable problems. Okay, so in the previous box volume optimization, we had an objective function like this. Okay, so let us draw the contours of it using MATLAB. Okay, so this is the surface which we saw in the last class, and we found the maxima. Maxima was somewhere here. So what you can do is that in the MATLAB command, you can ask it to draw contours, and it will slice the objective function at various altitudes. Okay, so let us look at this. Okay, if this yellow line is contour for f is equal to 15. Okay, that is this yellow line. So at f is equal to 15, the thing is sliced like this. Okay, the thing is sliced and the projection comes down. Okay. So this is f is equal to 15 contour. Okay. Then here f is equal to 25. Okay. 25, 27, 20, etc. So 20 is like this, and you have to slice it at f is equal to 20, and this cross section is the contour, and that has to be projected down. So the contours are projected on the xy plane. So once the oh, oh, contours are obtained, there is no need to look at this three-dimensional graph. Okay. Okay, so these are the contours which are projected on the xy plane. So frequently we will not be given the actual shape of the three-dimensional objective function. We will only be given the contour. So looking at the contours, we can see the increasing value of objective function. Okay, f is equal to 15, f is equal to 20, f is equal to 27, 25, 27. So, okay, the maxima will be here. Okay, maybe f is equal to 30. That dot will be the maxima. So, looking at the contours, now just like doctors look at X-rays, we can find the maxima. Okay, then just one example. Plot the objective function of the plot the objective function surface and the contour. So this is the objective function, and the range is -2 to 2. X range is -2 to 2, Y range is -2 to 2. So let us plot the objective function surface first, and then ask MATLAB to draw the contours. So you have to remember this code. Okay. So when I give first assignment, you have to use MATLAB. So you have to study MATLAB also. So this is the command to plot the objective function surface. Okay. First, you have to obtain the XY grid by this command. Okay. So in this command, you are saying that X and Y, the range is from -2 to +2 in steps of 0.1. Okay. You have to give the grid step size. So in steps of 0.1. Okay. So this command will draw the grid. So suppose this is X, this is Y, this command will make the grid like this. Okay, from -2 to +2 with a gap of 0.1. Okay, so this next command calculates the altitude at each grid point using this equation. So you can see that exponent of minus, so this term is programmed here. Okay. So when you type this command, it will calculate the altitude, Z altitudes of all the grid points, and it will draw the surface like this. Okay. Okay. So this is the Z values of each grid point. Okay. So this Z command will calculate all these Z values. Okay. Then you type mesh XYZ, and it will form this mesh. It will form this surface mesh. It will form this surface mesh. Okay. So this is the 3 steps. First you make the grid, then you specify the altitudes at each grid point, then you give the mesh command. So this is just the X label and Y label. Okay. Okay, so you got this objective function surface. Next is the contour command. Okay, so this is how the objective function surface looks like. Okay, then with the contour command, we have to specify how many slices the objective function has to be sliced to get the contour. So the contour command is you have to input the previous values of X, Y, and Z, and you have to specify n. So in this example, I'm setting n equal to 10. Okay, so the altitude will be sliced into 10. The objective function will be sliced into 10 altitudes with equal gap, and it will project the contour, project the slices here as the contours. Okay, so here you can see that this yellow and red are altitudes which are above the xy plane, and this the green and blue are altitudes below the xy plane. Okay, so this is above the xy plane, and these blue regions are below xy plane. So you can see that 0 is this xy plane. Okay, this is the xy plane. Okay, so all these slices above the xy plane will come in red, and below the xy plane will come in blue. Okay, so that is what you see here. Okay, so looking at it, you can see that that f is equal to 0.1 here. So it is 0.35 here. And if you take more slices, maybe you should take 100 slices. Okay. Okay. If you take more slices, it will come like this. Okay. And you can see that minima will be somewhere here. Maybe at f is equal to 40, you will get the, get the maxima. Okay.
Really maximum.
And what? Okay, maxima will be here, and what will be the xy value? So x will be like 0.8, and y will be like 0. Okay, y will be 0. That is where maxima will occur if you look at contours. Okay.
Sir, if the range is extended to a sufficient size, then it will become a point probably, sir, right? For the
Huh?
maxima. What I mean to say is, if you go to the
No,
previous,
y is 0 because this is actually symmetric about the y-axis. So maxima will occur only here. Okay, y will be 0, and x will be roughly around 0.8. Or what did you say? 0.2 or something?
no, sir, I told sir, basically the maximum point will reduce to a point. It will just be a point on the contour,
Yes, yes, yes. Yeah. So it can come here also.
right, sir?
Because I'm just doing some interpolation. Because it can be like here also. 0.6 also. So this is graphical method. So that's what I was trying to say. Okay. So now we can solve this graphical optimization problem in 2 variables. So this is a somewhat simple problem. Okay. But to solve this, you need to use MATLAB. Okay. But for exam, similar types will be asked. So find the minima of this objective function in 2 variables, that is x and y, and 2 constraints are there. Okay. Okay. So first you have to draw contours of objective function. Okay. So to how to draw contours of the objective function. So objective function has to be sliced at different f values. As you know, f of xy is equal to this. So you have to put various values of f: 0, 1, 2, 3, 4, etc. Okay. So these are the various slices. Okay. So for this particular example, if you look carefully, this is the equation of a circle with center 1, 1. Okay. And this is actually r squared the radius. Okay, first slice is okay. Let us look at second slice. Second slice is a circle which is centered at 1, 1 and a radius of √1. Third slice is circle centered at 1, 1 and radius is √2, and so on and so forth. So it will be like this. This is 1, 1. Okay, this will be the contours of this objective function. Okay, so it will go like 1, 2, 3, 4, etc. And the f is equal to 2, f is equal to 1. Okay, so this is how the objective function looks here. Okay, but we will draw with the MATLAB this. Okay, so if you draw the surface of this objective function, it will look like this. Actually, for your problems, there's no need to draw the surface and all. Okay, and if you slice it at various heights, you will get this concentric circles. Okay, but we already saw how we get this concentric circles. Okay, because they are circles centered at 1, 1. Okay, so when you project the contours on the xy plane, they look like circle centered at 1, 1. Okay, so x is equal to 1, y is equal to 1. Okay. So in the MATLAB, I have written this equation and I asked it to slice into 10 or 20 altitudes, and that is how I got this picture. Okay, but you can draw it with compass also. This type of simple contours you can draw with the compass for the exam. Okay, next is to impose feasible region on the contours. So you have to find feasible region of the two constraints G1 and G2. So first let us draw feasible region of G1. So equation of G1 is x minus 3 whole squared plus y minus 1 whole squared minus 1 is less than or equal to 0. Okay, so this is what you see here is the boundary. Okay, boundary is actually my x minus 3 whole squared plus the y minus 1 whole squared minus 1 is equal to 0. Okay, so all points on the boundary satisfy this equation. This is actually a circle with center 3, 1 and radius of 1. So if you put equal to 0 means all the points will lie exactly on the circle. Okay, and if you say the points are say less than or equal to 0, which is what we want, it means that the points will lie inside the circle. So our constraint says that every point should satisfy the equation such that this x minus 3 whole squared plus y minus 1 whole squared minus 1 should be less than or equal to 0. So okay, so this means that all the points are inside the circle. And suppose the constraint says it should be greater than or equal to 0. So that means that point should lie outside the circle. Okay. Okay, but that is not our case. Our case is the point should lie inside the circle. So that's the first constraint, first feasible region. So next constraint is 2x minus 5 should be less than or equal to 0. So how do you draw this feasible region? So first you draw the line equality constraint 2x minus y minus 5 is equal to 0. Okay, so this is the line, it will have infinite length. Okay, so this will divide, this line will divide the xy plane into two halves. On one half it will be 2x minus y minus 5 is less than 0, and on this other half will be 2x minus y minus 5 will be greater than 0. Okay, so how do you know which is which? Okay, why should this occur on the left side and why should this occur on the right side? So that you can do by sampling a point. You take a sample point here, x equal to 0, y equal to 0, and you substitute in this equation. Okay, 2 into 0 minus 0 minus 5. So that will give minus 5. So minus 5 is less than 0. So this is actually the less than 0 side. Okay, less than 0 side. So how you know that is by sampling one point. You take one xy point on this left side and substitute in the equation of the line and see if the right hand side is less than 0. So since you got minus 5, this is the area we want. Okay, then automatically this becomes the side where 2x minus 5 is greater than 0. That also you can check. Okay, you take a point here. Okay, so here y equal to 0, x equal to plus infinity. Okay, one point here. You substitute it 2 into infinity minus 0 minus 5. So this will give
Infinity.
plus infinity, so positive. Okay, so this is the greater than or equal to 0 side. Okay, so this is how you draw the feasible region. So now you have to superimpose both of these feasible regions. Okay, so this thing and this thing has to be drawn on the same graph paper on the same scale, and you can see that This is the feasible regions. Okay, so all these points will satisfy the straight line equation, this straight line constraint as well as circular constraint. So we need only consider points in this semicircle. So the center of circle is 3, 1. Okay, just for, okay, 3, 1. Oh. So next we have to superimpose the contours on this objective function contours on it. Okay, so you can, so we know that the objective function contours are centered at 1, 1 and they go increasingly like this. Okay, 0.4, 0.8. So the contours are increasing like. So we find that the contour f is equal to 1 or objective function value equal to 1 just touches this feasible region. So this is the minimum value of objective function. Okay. Okay. And the objective function value is 1 and the actual xy value is, so x is equal to 2 and y is equal to 1. Okay, that is the xy value. The what is the maximum? Okay. Okay, so you can draw further contours like this. Okay, all these contours will have larger values. So the largest value of objective function which just touches the feasible region is f equal to 6.4. So this contour is f is equal to 6.4 and it just touches the outer limit of the feasible region. Okay. And this value of x is 3.4 and this value of y is 1.8. Okay. Okay, you can have contours like this also. F is equal to 7, 8, 9. So these are all large objective function values, but unfortunately they are not touching our feasible region. Okay, so these objective function values are not acceptable to us since they don't touch the feasible region.
Sir, if 4 is missing,
Hello, can you repeat?
You're not audible.
Hassan, you are not audible.
Okay, okay.
am I audible?
Now some echo is there. Maybe you are using two devices.
Sir, why this minimum can't be of this at this level? What I meant to say at this level, where the what I meant to say a mirror of the point which is the maxima of the function. This could also be a
Here.
minimum.
This place, huh?
Yeah, this place, sir. What I mean to say is intersection of line and the circle. If we expand the contour of this function, it probably will touch over here and it can give the minimum value.
No, no. This is the shortest radius of this is the shortest value of objective function which touches the
Okay, got the point.
feasible region. So this is the maximum value of objective function which just touches the feasible region. So
Got it,
this
sir,
is
got
the
it.
minimum.
Got it,
This
sir.
is the maximum. Okay.
I'm sorry. Got it.
Okay. Okay, we can stop here and some more engineering examples we look in the next class. Okay. Let us stop.
Sir, just one query. Hello?
Okay, let us see if recording is still going on.
Sir, am I audible? Hello?
Okay, it is going on now.
I think some problem.